it's called the method of initial rates. It is one way of determining the rate law, right? Essentially determining what those orders are. They have to be determined experimentally. There's no way just looking at an equation that we can figure out what those orders are. We have to do an experiment to figure out how it works. We'll talk about why that is. So again, with our simple A becoming B reaction, all we have to do is record concentration of A versus time. Okay? So some kind of concentration sensor. If it's something that's colored, we can use a colorimeter like we're doing in lab today. Or you can have other sensors, or it can be directly measured or titrated or whatever. Okay? But we need to record concentration versus time, okay, with A0. What do you suppose that means? What kind of concentration? Initial concentration. Okay. At different values. Okay. We start out the initial concentration differently, and then we record how that changes over time. So look at our graph here. 0.1, 0.2, 0.4. Those are the different initial concentrations that we started in our 3 different experiments. Okay? And then all we have to do is zoom in on the initial part. Okay? So before the rate has gotten a chance to change, okay, because the concentration is changing over time, we just look initially sort of at the initial slope. Okay? And if our data is good, really all we have to do is just look at our first 2 data points, okay, if that's consistent. So what I've got over there are zoom-ins, okay, of those initial portions of the graph. Okay? And initial rate is just the rise over run of those initial portions of the graph. Okay? So you've got 3 values there. Rates are always positive, okay? But because A is a reactant, its concentration is decreasing, but the rate is going to be, the actual rate is positive. Okay? But you can tell sort of based on the slope of those lines that it correlates with those values there. Okay? And if we're just doing comparison, those are all 10 to the negative 3. So you just really need to look at the number in front, right? 5.58, 2.79, 1.40. Okay? So rate of 5, a rate of 2, a rate of 1. Okay? So the reaction is actually going the fastest in which of those trials? What do you think? Which one is the fastest reaction? Yeah, the one with the 0.4 initial rate. Okay, that's the fastest. That's the slowest. That's going to be important for us to remember. All right, so what we want to do, because our job here is to calculate n. Okay? That's the general format of our rate law. Rate is a rate constant times a concentration raised to an order or an exponent. Okay? All we have to do is set up the rate laws for any 2 trials. Okay? These are just 2 trials. Okay? We just happen to pick the 2.79 and the 1.40. Okay? And what we can do is we can divide these 2 trials. Okay. A lot of times when we're comparing 2 similar things, we can divide them to see what the actual what they have in common and how they're different. And a lot of things cancel out when you divide them, right? A lot of units cancel out. The power of 10 cancels. K cancels, because K is the same for any given reaction, okay, regardless of concentrations. Okay? K cancels. Okay? That unit cancels. Okay? So really all we're left with is the numbers. 2.79 over 1.40 equals 0.20 to the n over 0.10 to the n. And there's a distributive property of exponents like that where we could combine those 2 and just use that one common exponent for that. So what's 2.79 divided by 1.40 just in your head? Pretty much, what's that pretty much close to? Yeah, 1.40 times 2 would be 2.8. So with an experimental error, that's 2, right? So 2 equals, what's this part here? 2. N equals n equals 1. Okay, so that tells us that rate K, concentration of A, to the 1 power. What do we call that? First order. Okay. Now, that's a way of doing it with math. We can also do that with words. Okay. Looking at this trial to that trial, okay, that was double the rate. And this trial to that trial, it is also double the concentration. Okay. If the rate and the concentration have the same relationship, that's a first order reaction. That's the rate and the concentration being directly proportional to each other. So if you double one, the other doubles. Okay. That's what happens in a first order reaction. What we can also do is use any trial's data, substitute that into the rate law, and we can get the rate constant, K. Let's just pick one of them. Here, let's rewrite our rate law. Rate constant, concentration, first power. Okay. Let's pick any one. Let's just pick the small one. The rate, or that initial rate, 1.40, 10 to the minus 3. But we could have picked any of them. But let's keep these units. K. Concentration of A, 0.10. Okay, just the 1 power. I just picked 0.10 because we can do that in our head. Divide by 0.1, 1.40, 10 to the minus 2. Okay. But what unit would that K have? Let's think about that. Okay, so what did I do to 0.10 m to get K by itself? So what did I do with that 0.10? I divided both sides by that 0.10, right? So that m would cancel, right? So, yeah, per second, right? So you could call that S minus 1. Okay, that's pronounced per second. The unit of K is different for different reaction orders. For instance, if we had second order, we would now have 2 molars here. And you'd divide down there, but only one of them would cancel out. So you'd still have one of those molars left over. We'll do one of those in just a little bit. But you actually have to do that algebra to figure out what units remain, what units are left over for the rate constant for that reaction. Okay. All right, so the reaction that I showed you here with these graphs, that's first order, right? So it's not straight, it's curving, but it's gently curving, okay, over time. On the next page, look at these graphs for 0 order and second order reactions. What do you notice about the lines on a zero order reaction? They're straight. They have a constant slope, which means the rate is unchanged. And look at those values for initial rate, regardless of the concentration. Okay? Initial rate is the same. Okay? Those all had the same slope to them. Okay? One way of just sort of describing that with words is that the rate is unaffected by concentration. And normally we think of concentration changing as the reaction goes along, and that changes the rate, but also initial concentration would sometimes affect rate, okay, but not in a zero order. Okay? All of these initial concentrations are different, but all of those initial rates are the same. Okay? So with rate unaffected by concentration, we could do a method of initial rates if we just, say, picked those ones. It's usually easier to have a larger value over a smaller value, but if I put those two rates over top of each other, and the two concentrations over each other, the rates are 0.014. And the two concentrations, 0.20, 0.10 N. N equals, as we would expect, N equals what? 0. But honestly, if it's zero order, I mean, this just sort of confirms it. But if it's zero order, you really should be able to tell just by looking at the values. Okay? If all the initial rates are the same, okay, regardless of what happened with our concentration, that means that concentration has nothing to do with the rate. Okay? That concentration could be anything. As long as there's some of it there, then the rate of that reaction would be the same. That's what happens in a zero order reaction. Okay? If we look at the second order reaction, and let's compare these ones over here, right? Remember, rate equals rate constant times concentration. So if we divide those two rates, 5.6, 1.4, 0.20, 0.10, I can already tell you that 5.6 over 1.4 looks like 4 to me. N equals. Okay. So what happened here, we doubled the concentration. That made a 4 times rate. Here, we doubled the concentration. Rate's the same. With first order, we doubled the concentration. What happened to the rate? It doubled as well. Okay? So, looking at doubling the rate, if it's possible, if you're the one controlling the data, doubling the concentration is a really nice, convenient way of looking at how the concentration, how the rate is affected by that. Okay? If doubling the concentration has no effect, it's zero order. If doubling also doubles the rate, it's first order. If doubling quadruples the rate, it's second order. Okay? Now, what if we have values that aren't quite as neat and tidy as those values? Let's say we did 1.4, 2.90. Like 2.96. Okay, so concentration, rate. A couple of values here. Let's say we did 0.1 and 0.2, just like those others. But rate was 1.4 and 4.1. Okay. Can already tell this isn't going to be quite nice and neat because 4 is 1.4 and 5.6, so this is going to be somewhere in between. Sometimes those orders are not integers. Okay? We're going to have an example in lab today where there's a non-integer reaction order. So the way we handle that is we set it up the same way. Okay? We divide the rates. Okay? It's helpful to have the bigger one on top, 4.1 divided by 1.4. And then we divide those concentrations, 0.2 over 0.1 raised to a power. Okay. I did this before. I got 2.9286. Right? Does that look right? Okay. Now, what we did up above, we just kind of used our intuition. Right? We said what 2 to what power is 4. And if you got nice whole numbers like that, you can figure that out. Okay? But if you got something weird like this, even sometimes if it's a whole number exponent, but your values are really weird for some reason. Maybe you didn't have a choice of what concentrations to pick, and it was 1 molar and 1.3 molar or something like that. Okay? What math? How do we do math to solve for an variable that's inside of an exponent? Any ideas? Ooh, we need to involve logarithms. Okay, log. And any log will do here, whether it's a common log or a natural logarithm or whatever, but just pick one. Okay? We usually just use regular log, but okay. And we could just say log 2 to the n, but that doesn't really get us anywhere. Anybody remember the unique thing that happens when we have an exponent that's inside of a logarithm? E. E is the opposite of the natural logarithm. There's a unique property, there's a unique behavior that happens with that exponent. The exponent comes out in front. Okay? So we could just say log 2 to the n, but in fact I'll write that. But that equals n log 2. It may have been a while since you've seen that in your algebra class, but that's how you get a variable out of an exponent, okay? By taking the logarithm of both sides, okay? And it has to be pure on that side with the exponent. It has to just be something to that power, okay? But if you take a logarithm of it, that exponent comes out in front, okay? That's one of the key definitions of logarithms, property of logarithms, okay? So, then what? How do you solve for n? If we got this, and we don't have that anymore. What do we do? If I have log of that value equals n log 2. Divide. N equals log of that number. 86 divided by log of 2. You cannot take the log of that fraction. You have to take the logs of them individually. If you wanted, you could take the log of them subtracted. That's a funny thing that logarithms do, because those logarithms are really the exponents. That's the whole idea there. When you divide exponents, you subtract them. But just easiest to keep it totally like that. Anybody get an answer? This one? Log 2.9286 divided by log 2. And you could have used any logarithm. What did you get? 1.55? And what does that value actually mean? What is that one? Where would we put that 1.55? That's the exponent. Rate equals, okay, concentration of the reactant to the 1.55 power. So you can use that method if you've got a non-integer exponent, or you can use that method if the numbers are just weird and you can't see it in your head. Okay? Most of the cases in your problems and stuff like that, it'll be nice numbers, but there are times when you need to actually do that math. And the only thing really that's required is using that logarithm trick where you can bring that exponent out in front of the logarithm. Okay. Yes?
I had actually originally brought in 2.9286 to 3. And I took 3 divided by 2 and I got 1.5 still.
3 divided by 2, that might be a coincidence. Careful with that. I don't think that means anything. You can't just like cancel out the logs over there. So. Okay.
Wouldn't that be rounded to 1.6?
Yeah, probably. All right. Anybody have other questions about that? Okay. So let's add some more reactants. Okay. Here we have A plus B makes C plus D. Okay. Lowercase, I've got their coefficients there. Rates for when we have multiple substances there. Still, it's almost always going to be just in terms of the reactants. Okay. M and N, experimentally determined exponents. And this method of initial rates, is how one way that we can determine them experimentally. Okay? So here are two reactants, I minus, ClO minus, OH minus up above the arrow. What does that usually mean something is when it's above the arrow? It is a catalyst, and I think I said cat right there. Okay? But we said that the catalyst concentration can influence the rate, so that's usually included in the rate law as well. Okay? So we did several reactions. We varied the initial concentrations of each of those things, and we sort of did that in a systematic way. Okay? And sometimes it's up to you to figure out what kind of happened. We didn't necessarily rate them in order here. If you were designing that experiment, you would maybe start out with them all the same, and then you would change one, and then you'd change the next one, you change the next one, but kind of only changing one thing at a time to limit your variables. Okay? The general format for the rate law is down there. There's a constant. There are each of the concentrations of those reactants, and we use M, N, and P. Okay? And then it goes alphabetically after P. Why do you suppose we never use lowercase o as a letter for an exponent? Because it looks like a 0, because it looks like initial. Okay? So we don't use L because that looks like 1. Okay? So you very commonly see M, N, P, Q, R for exponents, so they don't look like numbers. Okay? So find pairs of trials where only one concentration changes to figure out the orders of M, N, and P. So for instance, let's do M together. Okay? And then I'll let you try the other ones. M is for iodide. Which are the two trials where I minus is the only thing that changed? Which are the two trials where I minus is the only concentration that changed? Two and 3. See what we're seeing there? Okay. There we've got a change of those concentrations, but the other concentrations are the same. Okay? You have to choose a pair of trials where the thing you're interested in is the only difference. Okay? That's important. So I'm going to do 2 over 3, so I can have a large one over a small one. Okay? So let's write this like this. Experiment 2 over experiment 3. Okay? And then we're going to start with their concentrations, or I'm sorry, their rates divided. And if the power of 10 is the same, you can just leave it off. I'm just going to say 12.2 divided by 6.1. Okay? and then their concentrations in the parentheses, 0.020, 010 m. You should hopefully be able to just kind of look at those values and tell me what the exponent m is. What do you think it is? Yeah, m is 1. Okay? Because 12 over 6 is 2. 0.02 over 01 is 2. 2 equals 2 to the 1 power. M equals 1. That means the reaction is first order with respect to I minus that reactant. And I just write it that way because that's always how it's said, just so you know what that means. Okay. So here we got just a few minutes left. Why don't you see if you can find the relationships, okay, that can have n being the only thing that changes, and then p being the only thing that changes. Let's see if you can figure out those. In each case, it's the rates divided, it's the concentrations divided inside the parentheses with the exponent. Okay? So give that a try. But remember, it has to be a pair of trials where that substance you're looking for is the only thing that's changing. Everything else has to be the same, otherwise it doesn't work. Which two experiments did you use for n? Yep, that's the CLO minus. Should have used 1 over 3. That was 6.1. Concentration changed. Concentration changed, but the rate didn't change. Okay? That should tell you something immediately. What does that mean? Zero order, right? 1 equals 2 to the n equals 0. Which 2 did you use for P? That is the OH minus. Should have used 4 over 3 to get a positive, to get a bigger number here. 24.4 over 6.1. That's 0.02, 0.01. Okay. P equals what? So overall, rate constant, concentration of I minus to the what power? Yep, that's M. Okay, so I'm just going to say I minus. Okay, and then what about the CLO minus? That's what power? Yeah, it's 0 power, so we're not going to include it here. Okay, something to the 0 power is just 1. Okay, but then the OH minus 2. Okay, that's I minus. That's CLO minus. That's OH minus. That is the rate law. And again, there would be no way we would have been able to tell that just by looking at the chemical equation. The reactants, the catalyst, the product. Has to be determined by experiment. Turns out that it's first order with the iodide. Concentration of the CLO minus has no effect on the rate. Okay? Second order with the hydroxides. Hydroxide has an extra effect on the rate. Okay? So, good place to stop. See you all in lab in a few minutes.